Hello everyone. In this lesson, we are going to discuss about magnetic properties of coordination compounds. In content, we will cover Introduction, Types of magnetic behavior, ferro and antiferromagnetic coupling, spin orbital coupling, and spin crossover. Introduction. The magnetic behavior of coordination complexes can be easily explained using crystal field theory. In general, the ligands, having very high splitting energy, leads to the formation of low spin complexes, since the gap between T2G and EG level is much higher. However, for low field ligands, splitting are less, and thus, they lead to the formation of high spin complexes. Since the complex hexacyano-iron 2 is diamagnetic in nature, so its magnetic moment is 0, but for the hexa-aqua complex, it can be calculated as follows. For hexa-aqua complex, N is equals to 4. So, mu s is equals to under root of 4 into 4 plus 2. That's become equals to 4.9 Bohr magneton. Observed mu effective for the high spin complexes of iron 2 plus is 5.10 to 5.70 Bohr magneton, which is very close to spin-only magnetic moment. Consider the complex, first hexacyano-iron 2 plus complex, and hexa-aqua-iron 2 plus complex. In both the cases, Fe is in the plus 2 oxidation state, and has octahedral geometry, but the complex with cyanide as ligand forms a low-spin diamagnetic complex, where all the electrons are paired up, whereas the complex with H2O as a ligand form high-spin complex. Cyanide is a strong field ligand that leads to high amount of crystal field splitting, and thus forms low-spin complexes, whereas H2O is a weak field ligand, which give rise to lower splitting, and thus forms high-spin paramagnetic complexes. This difference can be seen in this diagram. We can see that the hexacyano complex has large splitting, as compared to hexa-aqua complex. There is no unpaired electron in case of hexacyano complex, as compared to hexa-aqua, where we have 4 unpaired electrons. So, hexacyano complex is diamagnetic, whereas hexa-aqua complex is paramagnetic. The calculated and experimental magnetic moments for complexes of 3D transition metal ions are shown in the table. There are 4 types of magnetism. First one is diamagnetism. Diamagnetism is found in elements with paired electrons. For example, silver, copper, gold, lead, zinc, etc. Such a substance allows a smaller number of lines of force to pass through it, and therefore prefers to move to the region of lowest magnetic field strength. Diamagnetism is a very weak form of magnetism that is only exhibited in the presence of an external magnetic field. It is the result of changes in the orbital motion of electrons due to the external magnetic field. The induced magnetic moment is very small, and in a direction opposite to that of the applied field. When diamagnetic materials are placed between the poles of a strong electromagnet, diamagnetic materials are attracted towards that regions where the magnetic field is weak. Second one is paramagnetism. In paramagnetism, the atoms or molecules of the substance have net orbital or spin magnetic moments that are capable of being aligned in the direction of applied field. This alignment of the atomic dipoles with the magnetic field tends to strengthen it. Paramagnetism occurs in all atoms and molecules with unpaired electrons. Example: free atoms, free radicals, and compounds of transition metals containing ions with unfilled electron shells. It also occurs in metal as a result of the magnetic moments associated with the spins of the conducting electrons. For example, aluminium, chromium, molybdenum, sodium, titanium, and zirconium, etc. In most paramagnetic substances, the magnetic properties originate entirely from the individual magnetic centers, that is, there is no secondary magnetic interaction between the neighboring magnetic centers. Such a substance is called magnetically dilute substance. There are some paramagnetic substances in which secondary interaction exists between the neighboring magnetic centers. Such a substance is referred to as magnetically concentrated, and the interaction in it may lead to an increase or a decrease in the magnetic moment. Third one is ferromagnetism. It is a phenomenon in some magnetically ordered materials in which there is a bulk magnetic moment and the magnetization is large. The electron spins of the atoms in microscopic regions, which is known as domains, are aligned. In the presence of an external magnetic field, the domains orient favorably with respect to the field grow at the expense of the others, and magnetization of the domains tends to align with the field. The total magnetic moment of a substance is the vector sum of the magnetic moments of component domains. Ferromagnetism is a phenomenon by which a material can exhibit a spontaneous magnetization, and is one of the strongest forms of magnetism. It is responsible for most of the magnetic behavior, and is the basis for all permanent magnets. Last one is antiferromagnetism. It is a phenomenon in some magnetically ordered materials in which there is an anti-parallel alignment of spins in two interpenetrating structures, so that there is no overall bulk spontaneous magnetization. In ferromagnetic materials, it is energetically favorable for the spins atomic to align, leading to spontaneous magnetization. However, in antiferromagnetic materials, the conditions are such that it is energetically favorable for the spins to oppose, leading to no overall magnetization. In materials that exhibit antiferromagnetism, the spins of magnetic electrons align in a regular pattern with neighboring spins pointing in opposite directions. This is the opposite of ferromagnetism. Antiferromagnetic materials have a negative coupling between adjacent moments and low frustration. Antiferromagnetic materials are relatively uncommon. An example is the heavy fermion superconductor. Spin orbital coupling. As we know that some of the First transition series metal complexes, example, low spin iron 3+, high spin iron 2+, and cobalt 2+, give magnetic moment, much higher than, calculated from the μs equation. So, every metal ion, except for D1, D2, the low spin D5 and high spin D6, and D7, follow spin-only formula. In most of the transition metal complexes, the motion of electrons is very much restricted, so that, effectively orbital magnetic moments quenched. The unpaired electrons, in a first transition series metal ion, are located in the 3d orbitals. A transition metal ion has 5 degenerate 3d orbitals. In order for these electrons to the orbital magnetic moment, the electrons should go around the nucleus via these orbitals. In such a case, spin-orbit coupling takes place and contributes to the overall moment, that is, mu effective is greater than μs. Spin-orbit coupling is the interaction of an electron's orbital angular momentum and its spin angular momentum, leading to a magnetic moment. For spin-orbit coupling to occur, the following 3 conditions must be satisfied. Number 1, there must be a half-filled or empty orbital, similar in energy to the orbital holding the unpaired electron. Number 2, there must be a half-filled or empty orbital, similar in shape and symmetry, that is, they should be transformable into one another by rotation about same axis. Number 3, the nearby symmetry-related orbital must not contain an electron with the same spin as the first one, according to Hund's rule. Electron in this orbital can make use of nearby orbital vacancy by moving into it around the center of the complex and generate orbital momentum, which leads to additional magnetic moment. As we know that spin-orbit coupling means S and L do not operate independently, and J states need to be defined. But spin-orbit coupling is usually small for lighter transition metals. We can treat S and L independently. This isn't true for heavy metals and their magnetism, as it is much more complicated to predict. Ferro and antiferromagnetic coupling. As we have already discussed that the anomalous magnetic moment is the magnetic moment for a metal ion in a discrete molecular species, having a value which falls outside the range of values predicted from considerations of the spin and orbital angular momentum in ligand fields of given strength and symmetry. For such systems, magnetic property of a metal ion is influenced only by the ligand field. Anomalous magnetic moment may also arise in magnetically concentrated systems. The magnetic interaction in a complex occurs when the neighboring centers are close enough for direct or indirect orbital overlap. This interaction affects the magnetic property of the complex and the ligand field effect. In fact, almost all paramagnetic complexes, to a certain extent, are involved in exchange interaction, which is dominant only at low temperatures. When the exchange interaction energy is greater than kT, the result is a cooperative phenomenon of ferromagnetism or antiferromagnetism. The magnetic moment of a complex involved in an exchange interaction may be more than or less than that of a complex, not involved in the exchange interaction. The former situation is a characteristic of a ferromagnetic substance, whereas the latter is a feature of an antiferromagnetic substance. So, there are two types of magnetic exchange coupling. One is ferromagnetism. Second one is antiferromagnetism. For ferromagnetic substances, the neighboring spins align parallel to one another below a certain critical temperature, Tc, which is known as Curie temperature, and below Tc, the material remains permanently spin-aligned, even when the field is removed. It is a field-dependent effect. For antiferromagnetic substances, the neighboring spins align antiparallel with one another below a certain critical temperature, Tn, which is known as Néel temperature, and below Tn, the material tends to remain spin-aligned, and has a lower moment than expected. The coupling forces are responsible for the alignment of the magnetic spins. In an antiferromagnetic substance, the neighboring magnetic centers are opposed to each other, but in ferromagnetic substance, they are aligned parallel. The spontaneous alignment of magnetic dipoles in ferro or antiferromagnetic states need some positive energy of interaction between neighboring spins. Spin crossover. It is a phenomenon that occurs in some metal complexes, where the spin state of the complex change due to external stimuli such as a variation of temperature, pressure, light irradiation, or an influence of a magnetic field. Spin crossover refers to the transitions between high to low, or low to high, spin states. This phenomenon is commonly observed with some first-row transition metal complexes, with the d4 to d7 electron configuration in octahedral ligand geometry. As we already know that metal ions with any of the d4, d5, d6, and d7 configuration exhibit two possible electron configurations, that is, high spin and low spin state, in the octahedral ligand field. These high spin and low spin states of an octahedral complex will have the same energy when delta is equals to P. If in a coordination complex, the crystal field splitting is close to the delta is equals to P value, then the energy difference between the two spin states of the complex will be in the range of thermal energy kT. Further, in octahedral field, if the energy of the two spin states is same, or nearly same, the low spin and high spin states can coexist in equilibrium. This phenomenon is referred to as spin state equilibrium. That means the magnetic moment for these complexes will be anomalous. An example of metal ion that can exist either a high spin or a low spin state is Fe3+. In octahedral ligand field, depending on the ligands, they are coordinated to this complex. Fe3+ can attain a low spin or a high spin state, as we can see in the diagram. Consider the low spin complex, hexacyano-iron 2+ complex, and the high spin complex, hexafluoro-Fe2+. The Tanube-Shuganov diagram of two complex is shown here. Now, change in the temperature will lead to an alteration in the population of the two spin states. The Taneubi-Shuganov diagram of the two complexes reveals that, if the ground state of the complex is low spin, then an increase in temperature will increase in the population of the high spin state, that is, the magnetic susceptibility will increase. And a decrease in temperature will increase in the population of the low spin state, that is, the magnetic susceptibility will decrease. The Taneubi-Shuganov diagram of these D6 complexes also show that, near the crossover point between weak and strong field, the difference in energy between the spin-free and spin-paired ground states becomes very small. Within this region, it is reasonable to expect that both spin states may coexist in equilibrium, and that the degree to which each is represented will depend on the temperature. Spin crossover phenomenon can be represented by spin transition curves. In spin transition curves, T is plotted versus high spin molar fraction. These curves indicate that a spin transition has occurred in a metal complex as temperature changed. The gradual transition curve is an indication that not all metal centers within the complex are undergoing the transition at the same temperature. The most interesting example of spin crossover is shown in the graph. At high temperature, this complex exists as high spin with 4 unpaired electrons, and a moment consistent with 4 unpaired electrons is observed. But as the temperature is lowered, a sharp drop in magnetic moment is observed at 175 K, and the low spin form of the complex becomes dominant. This indicates that, at 175 K, complex exist as both high spin and low spin complex. Thus, the magnetism of complex changes sharply at 174 K. Thank you.